Right, Fig 8.1 shows a simplified diagram of an alternating current generator. Right, state the names of the components PQ and XY. Right, P and Q are slip rings. We call them slip rings. X and Y, those are carbon brushes. Carbon brushes. Right. Explain why an electromotive force EMF is only induced when the coil is turning. So this probably based on what to call this guy, Faraday's law and Lenz probably. So the EMF can only be produced when the coil cuts the magnetic field, or when the magnetic field is cut by the coil. So that's why EMF is only induced when the coil is turning. Right, so EMF, right, you're explaining why an electromotive force is only induced when the coil is turning. Right, this is because the magnetic field will be cut during the turning. Okay, otherwise if there is no turning, there is no cutting of the magnetic field. State one possible change that causes a larger EMF to be induced. You can increase the speed of rotation, increasing the speed of rotation. Right, we can increase the speed of rotation if you want to, or you can use a stronger magnets, right? Stronger magnets. This will bring about a very strong magnetic field, very strong B field. A magnetic field is normally represented by B. Right, some say you can also add more turns on the coil. Right, so yeah, you can just state one there. Alright, yeah, we'll switch on to something else. Fig 8.2 shows a circuit diagram. Right, so resistors A, B, C, and D are identical. This is very key to capture. The current in the resistor A is 2.4 amps. So if we have 2.4 amps coming through this one, it means we also have probably 2.4 amps passing through this one. Right. It's quite interesting because if these guys are identical, then what it means is that we have double resistance there. So if you have double resistance, what happens to the current? Remember, current is going to drop from Ohm's law. V is equal to IR. Right, so if you double this one, it means you're going to halve the current, like we have I being equal to V over R. So if you are doubling this one, it means the current is going to drop by half. So that means probably the current passing through these two guys is 1.2 amps between these two. All right, and remember, since they are connected in parallel, it means the voltage across A is the same as the voltage across A and B, so B and C, and then the voltage also across D is the same as that one in A and in B and C. Okay, so that's what we have there. State the value of the current in the resistor B. Explain your answer. Okay, so I've already highlighted that, right? The current in resistor B is actually 1.2 amps. It it must be half of current in A, since we have doubled the resistance through B and C. Okay, must be 1.2 amps there. Right, calculate the value of the current. So the value of the current is actually the current in the whole circuit, total circuit. That means you're adding 2.4 plus 2.4 plus 1.2. Total current I is equal to 2.4 plus 2.4 plus 1.2 plus 1.2. Right, this will give us what? 4.8 plus 1.2. This is 6 amps. So the total current there is 6 amps in the whole circuit. 6 amps. Alright, let's go down. The reading on the voltmeter is 5 volts. Calculate the resistance of A. So you realize that if you go back there on the diagram, right, we are told that we have 15 volts. So the 5 volts, we have 5 volts here. So if this is 5.0 volts, it means we have 5 volts on this one. Between these two is also 5 volts, and we also have 5 volts there. So if you want to calculate the resistor A, we're going to use Ohm's law. We are using Ohm's law there. So that means we have V equals I times R. So R will be equal to V over I, which is 5 divided by 2.4. Right, so what does this give us? R is equal to 5 divided by 2.4. This will give us 2.0833, which is approximately 2.08 ohms. 2.08 ohms. Right, this is what we have. I hope we learned something from this one. Thank you for watching again. Please